Hello! In this video we will talk about angular momentum, and we will explore the consequences of the conservation of angular momentum. Previously we have seen linear momentum, which is just the mass times the velocity. We also discussed that not only does a single particle have a defined momentum, but we can also define a momentum for a group of particles by simply adding together the momenta of all the particles in the system. Finally, we had learned that if no forces from outside the system act on any of the particles in the system, then the momentum of the system is conserved. This means that the initial momentum equals the final momentum, no matter what changes happen with all the individual particles. With angular motion, we can define a very similar concept, called the angular momentum. It is defined as the moment of inertia times the angular velocity. You can see the similarities, since I is the rotational equivalent of mass, and angular velocity omega is the rotational equivalent of velocity. Also, just as we can talk about the linear momentum of a system of particles, we can also talk about the angular momentum of a system of particles, which we will denote with a capital L. It is simply the sum of the angular momenta of all the objects in the system. Finally, if no external torques act on the objects in the system, then the angular momentum of the system is conserved, which means that the initial angular momentum equals the final angular momentum. You may not have yet seen the video on torques, but for now you just need to know that a torque is related to a force and is the rotational equivalent of a force. This conservation law is a very important concept, and is a large part of the reason why angular momentum is a useful concept. Let's take a look at two examples and see how the conservation of angular momentum can help us out. Imagine that two moons are orbiting a planet. The moons have the same mass, but one moon has double the angular velocity as the other, but in the opposite direction. Since these two moons are at the same radius away from the planet, they are headed for a collision. Let's assume that after the collision, they get smushed together into a single larger moon, and no mass is lost. What will be the angular velocity of the combined moon after the collision? Let's figure it out in terms of omega 1, the angular velocity of the moon on the left. Also, we are going to ignore any effects of gravity that the moons might have on each other. To solve this problem, we are going to use the fact that the initial angular velocity will equal the final angular velocity. After all, no torques are being produced from outside these two bodies. In case you're concerned about the gravitational effect of the planet on the moons as an outside torque, it happens to be that the gravitational force does not produce a torque in this case. If you have already learned about torque, you ought to be able to figure out why not. And if you haven't, then just take my word for it. So, let's start with the left-hand side of the equation. What is the initial angular momentum? Well, it is the moment of inertia of this body times its angular velocity, plus the moment of inertia of the other body times its angular velocity. Well, the moments of inertia are actually the same, since they have the same mass and radius of rotation. The angular velocity of the second body, though, is given by this formula here, so we just plug all of that in. On the right-hand side, we need the final angular momentum. After they collide, they will have the same radius but double the mass, so the rotational inertia is just double the mass times r squared. The final angular velocity is omega f, which is what we are solving for. So now the left-hand side simplifies to negative mr squared times omega 1. Next, both sides have an mr squared term, so those cancel. Finally, we just move the 2 over to the other side, and now we have that the final angular velocity will equal negative omega 1 divided by 2. That is to say, it will be half the initial angular velocity of the body on the left, but in the clockwise direction, since it is negative. Yay, we've solved for it. Let's consider another example. Figure skaters use conservation of angular momentum all the time. A figure skater starts off in this position, with her arms and a leg spread out. In this position, her rotational inertia is 10 kilogram meters squared, and her angular velocity is omega I, where I stands in for initial. She then tucks her arms and legs in close to her body. This reduces her rotational inertia to 5 kilogram meters squared, because now her mass is kept much closer to the axis of rotation. What will be her angular velocity after she tucks her arms and leg in? In this problem, we will say that any torque created by the contact between her skate and the ice is negligible, so there is no external torque. Therefore, angular momentum is conserved, and we write the usual conservation formula. Initially, her angular momentum is 10 kilogram meters squared times her initial angular velocity. After she tucks herself in, her angular momentum is 5 kilogram meters squared times her final angular velocity. Let's solve for the final angular velocity, since that is what we want to know. We just divide both sides by 5 kilogram meters squared, which results in this expression. Final angular velocity equals double the initial angular velocity. By tucking in, we see that she spins twice as fast. Great! We have seen how to use conservation of angular momentum to solve some real problems. Now I want to talk about how to relate linear momentum to angular momentum. If we have an object with a certain linear momentum, and we want to know what its angular momentum is around this axis here, how do we get that? Well, the angular momentum is given by this formula, which says that it equals the distance between the object and the axis, times the mass, times the perpendicular velocity. The perpendicular velocity means the component of the velocity which is perpendicular to r. To get what that component is, we draw this angle here, which I call A, and which is the angle between r and v. You can then break the velocity into a right triangle, whose hypotenuse is the velocity and whose legs are the parallel and perpendicular components of v. I suggest you pause here and work out the perpendicular component of velocity in terms of v and the angle A, since this is a straightforward exercise in trig. This is the answer you should have gotten. In general, you can use this formula to get the angular momentum in terms of the linear momentum. In the case where the angle is 90 degrees, or perpendicular, sine of 90 is just 1, so then we have this simpler formula. This formula can also be easily adopted to get the angular velocity in terms of a linear velocity, if that linear velocity is not simply a tangential velocity. To summarize, the angular momentum is given by this quantity, or perhaps by this quantity. Next, we can consider the angular momentum of a system by adding up the angular momenta of all objects in the system. Finally, if no outside torques act on the objects in the system, then angular momentum is conserved. And that's it for this video. Thanks for watching.